Hey, greetings everybody. Hopefully you can watch this before the Cowboys game or take a break. This is what we're going to work on tomorrow. It's more of a little review. Let's talk about some concepts, characteristics of functions. Um, we've got some graphs down here that we're going to look at. And one of the things you're going to ask is what represents an even function? Remember, even functions are, here's an example of an even function where this f of x, I plug in 1 and I get a 1, I plug in -1, I get a 1. And notice the symmetry about the y-axis, okay? So even functions, symmetric about the y-axis, okay? Odd functions, okay? This is kind of what an odd function looks like, but this is not one because it's not symmetric about the origin, right? Okay? Because if I take this point and I go through the origin, there's no point over here. Or if I take this point and I go through the origin, there's no point over here. If I rotate this 180 degrees, it will not map onto itself, okay? So odd functions are going to look like this. We'll notice this point here, or like this, point 1, 2, I go make a point right through the origin, I come to its counterpoint, -1, -2. If we rotate this 180 degrees, this will rotate on top of itself, okay? Odd function symmetry about the origin. Graphs that are always decreasing would look something like this. As x gets bigger, f of x, the output, or y, gets smaller. For the entirety of the graph, if you're talking about always decreasing, this would be that graph. Okay, for the whole domain, as x gets bigger, f of x gets smaller. Okay, the output gets smaller. So as x gets bigger, y gets smaller. Okay? Graphs that are always increasing, well, this graph is always increasing, even though, well, it kind of shallows out here, but it doesn't look like it's constant. This graph looks like it's always increasing. This looks like a logarithm graph that got shifted over. But notice, as x gets bigger, y gets bigger, okay? So that's always increasing, okay? Remember relative max and min. Here's a relative max. Remember, to have a relative or local max or local min, you have to have a change in direction, increasing to decreasing or decreasing to increasing. Remember, endpoints do not count as relative max or min. So here's a relative max, here's a relative min, okay? I'm looking for, remember, absolute. Here's a case where I've got a relative min, here's a relative max, here's a relative min, and that's also what? That's also an absolute minimum. Remember, you can be both. But here I've got a decreasing function or negative slope, and it changes to positive. So there's a relative min, and then I go increasing to decreasing, relative max. And here's another relative min, decreasing to increasing, there's a relative minimum again. But that's also the lowest value, the minimum value for the entire function, so that's also the absolute minimum also, okay? Right there is also your absolute min, okay? This graph does not have an absolute maximum. It's just got a relative, okay? And why doesn't it have it doesn't max out, it goes to infinity. These two ends go to infinity, okay? This graph is what? Let's see if we remember. Here's pi, so where my asymptotes are at pi halves. So would it be cosecant or secant is this graph? Remember, if the denominator determines the asymptote, and I've got asymptotes at pi halves, well, cosine 0 at pi halves. Okay? So notice how b1, 0, so this would be a graph of secant because cosine is 0 at pi halves, and that's where our asymptotes are increments of pi halves. Okay? That's an even function. We've noticed the symmetry about the y-axis. Talking about concavity. This is what? This is part of a frown. It's concave down. Okay? Concave down. Notice the tangent lines are above. If I made tangent lines, it'd be above the graph. This is concave down. Okay? This would be concave up. This is a smile until here's why am I drawing a blank here? The inflection point, that's what I meant to say. Here's my inflection point where I change from what? You change concavity from a smile to a frown, okay? Here we go. Here I go from a frown, concave down. This is part of a frown. Those tangent lines would be above to right here's my inflection point where I go to a smile. Now the tangent lines are below the graph on a smile. So right there is a point, inflection point. Inflection, boy, I can't seem to get that today. Inflection point, okay? So they'll be asking you things like graphs that are always concave up. Here's obviously a graph that's totally a frown, right? The whole graph. This graph right here is, it looks like a square root, so it's probably the negative square root. So you do a square root and the negative flips all the values over here. Looks like it's always going to be concave up. Looks like all these tangent lines are always going to be below it, okay? What are the parent functions for these graphs? Okay, that's something to think about, okay? This looks similar to tangent. Like I said, this talk square root, logarithm, things like that, okay? So that's all I have. What time is it? 6:30. Make sure you review your parent functions and like which label each graph with its parent function, what graphs are concave down, always concave up. So it should be a fairly easy day for us if we remember kind of a review from yesterday. All right, that's all I have. Have a great Sunday night, and we'll see you tomorrow. A lot of you are going to be out. I'll be out Tuesday, so we've got to make sure we watch the videos and so forth. Okay, I've got to judge a SAPIT or IPASS tournament on Tuesday. Go Cowboys! Bye.